Hands up. Boom, look how quick that is. So yeah, we just gave it a 1 second lag time now, which is plenty. Done. 1 minute, 1 second. Yes! I got a lot of coding to do, so let me just get right into it. The first program we're going to do is an exact copy of number files so we can get a grasp of what the program is supposed to do, essentially. So we're going to start out with an empty list, which is a grid. This is going to represent our Sudoku puzzle. Okay, so it's going to be a list of a list. And that essentially just means it's a list full of lists. Okay, so like a list, we have grid is equal to list, and then we have smaller lists inside the lists. The reason we're formatting it like this is for two reasons. One, so we can call columns and grid and rows, and two, for aesthetics, because look, this pretty much looks like a Sudoku puzzle already. There's really only two functions that we need to solve this. As you can see, this is an unsolved Sudoku puzzle. So what we're going to do is we're going to check if possible. And how we do that is not like how humans solve Sudoku puzzles. I thought this was quite interesting because when you're solving a Sudoku puzzle, you're looking for, or I don't know about you, but for me personally, I'm looking for things like this. Like, okay, there's a 3 here, and say there's like a 2 here, so that kind of cancels out that row, so 2 couldn't be there. And then let's just say, for instance, that there's a 2 here and a 2 here and a 2 here or something, right? And I'm like, oh, okay, so 2 can't be there, 2 can't be there, 2 can't be there. Okay, so 2 must be here. Boom. That's how I do Sudoku puzzles. And then of course you have like just straight up the numbers across the top. So if it's in the row, if it's in this box, and if it's in a column. So when we're programming this, we are going to take those 3 things into consideration. If it's in the row, if it's in the column, or if it's in the box already. So the box is, it's really tricky, but the row and column are pretty easy. So we're going to define this function by calling possible. And then we're going to pass in 3 variables. We have our x-axis, we have our y-axis, whoops. And then we have n, which is going to be, n is the possible number. So if we have x, we have a 0 and the x position is 5 here. See, x is going to the right and it's in 0. And then we have y, which is also 0. So 5 is represented on a grid as 0, 0. That makes sense? 0 in the x position, 0 in the y position. N is going to be represented like this. So the program's going to say, hey, n in position 2, 0. Can this be a 1? Okay, in this example, obviously it can be because there's no other numbers on the board, but let's just pretend that it can't be a 1. It can only be like a 5 or a 6. Okay, so it will try 5, and then if it finds out later that it wasn't a 5, it will backtrack and change it to a 6, essentially. So, but we're going to check first. So we're going to check the number in the columns first, and to do that, we're going to say for I in range 0 through 9. If you don't know much about programming and the I throws you off, it threw me off when I started learning Python, like really bad. The for loops are really confusing. Basically what we're saying is for whatever. Whatever, we can name it whatever right here. I can name this anything I want. I can say for numbers in range 0 through 9, that will work just fine. The I is just to make it smaller, really. That's all it is. We can call I later, too. So for I in range 0 through 9, excuse me, if the grid, which is what we named up here, this is our grid, index position I and index position X, we'll get to that in just a second. So what we're saying here is for the numbers 1 through 9, check in the X position, and if it's equal to N, we don't want it, right? Because it means that it exists in that row. That's all we're saying. It's a very codey way of saying that. But we can also say not equal to Y. And this will ensure that, whoops, and not equal to Y. So if it exists in the row, we don't want it. And if it's not equal to Y. Hey, editor Anthony here. This is a slip up. The code is absolutely right, but I just forgot to put and I is not equal to Y. Because if it's not equal to Y, then we don't want it. We return false. See, we say, no, stop. We don't want it. We're going to do the same thing for columns. So it's going to be the exact same thing for I in range 0 through 9. If grid, and then if you could guess, it's Y, not X. I, not equal to N, and I is also not equal to X. So don't worry about this part. This is checking, all you need to know for now is that this is checking rows, and this is checking columns. And if it exists in the row, return false. I don't want it. If it exists in the column, still don't want it. Right? This is how Sudoku works. Also, this is indented improperly. There we go. Okay. Now, how do we check the box? This is probably the most clever coding I've personally seen. And I'm not going to explain every single detail, but I will explain how it works. Mathematically, I'm not going to go into it because it's pretty complex, but I will show you how it's doing it, which is pretty cool. So, as you can imagine, how in God's name would I want to represent a number that exists here, right? N. Because I can check rows. Okay, if it exists in the row, don't want it. If it exists in the column, don't want it. But if it's a 1 and it's possible in rows and columns, how do I tell the program, hey, look right there. There's a 1 already here, can't be a 1. Because, as you can imagine, 1 can exist pretty much anywhere. It can exist here. So how do I tell the program, hey, look at every number around me, and if it exists, don't do it. Well, you might be thinking, well, that'll work, but it won't, because check this out. It can't work, because if N is right here, and you're telling it to check every number around it, then it's going to look here, it's going to look here, it's going to look here, and that's not right. If 1 existed here, 1 could exist here, right? It couldn't here and here, I know that. But if it existed here, then it can exist here. So how do I tell the program that? So this is where we get real tricky with our math here. So let me write out the function, then I'll explain it. And then after all that said and done, we're going to say return true, because if all that is checked, then it can be there. Okay, so let me explain this. So this function checks rows, this function checks columns, and this function checks the box. So this is really interesting. Basically, if n exists here, right? And again, this is represented by x4, y4. Okay, so this is 4, 4. Mathematically, it puts the box right here in the top left corner every time. It doesn't matter where in the box you are. You could be here, which is represented by x5, y2, and it will break down the math to stick to check from here, and then it checks for a 3x3 box. So this little conversion here is what I'm talking about. This is the meat and potatoes of the code. So n, which is represented by 4, 4. If I change this to 4, 4, then the first thing the program does is it says, hey, actually look here, which is represented by 3, 3. So if I print this, you see 3, 3 here. Okay. Now let's say that n is here, which is represented by x5, y5. We want to tell the program n's in this box, so let's check from 3, 3 in a 3x3 row to see if that number's in there. So we run this, 3, 3 again. Okay, whatever. You get the point. It works in the code, I promise. But yeah, that's how it does it. So no matter where it is in the Sudoku puzzle, it always checks the top left corner of that box. And then what this does right here is it creates a 3x3 grid. And then it just says if it's in that 3x3 grid from that top left corner, then return false. So that's all. It's kind of confusing, but that's how it works. Moving on. We can just use backtracking now, because otherwise we can say, hey, stick any random number here infinitely between 1 and 9, and eventually it will solve it, but it will take like forever to run. We want this to be quick. So this is where we have to create backtracking. So backtracking we can define by solve. This is also equally as sort of confusing, but it's worth understanding. So we're going to call global grid because we're working off that global grid, and we're going to say for y in range 9. Okay, and then we're going to say for x in range 9. So when we double up this for loop, we're basically we're isolating a number in the grid. That's all we're doing. And then we're going to say if grid with the index position y and x, doesn't really matter, but so now we're basically saying, hey, if this particular number equals 0, then we have to figure out what it is, right? Because you can't have empty spaces in here. If you noticed, 4, 0, 0, 0, 0, 5, 0, 0, 0. So we're telling the program, hey, if it's a 4, forget about it. It's already there. If it's a 0, though, we have to figure out what that is. That's all we're saying. Okay. So if it's a 0, and then we say for n in the range 1 through 10 is so we can not include 0. So what we're telling the program right now is if it's the numbers between 1 and 9. And then we can say if possible, and then we're going to pass in our x, our y, and our n. So now we're calling this function. We're saying, hey, if it's possible in that index that is currently 0, Then we're going to index y. We're going to index x. And we're going to make that equal to n, which n is currently just sort of a random number between 1 and 9, remember? So it's going to start with 1. If possible, put it there. Okay, if it's not possible, it will just return false. Pretty simple. However, as you know, when you're solving Sudoku, just because it can be there at the moment doesn't mean that is the correct number, right? So this is where backtracking comes into play. So this is actually like, and this is just super easy. Backtracking as an algorithm sounds like it's this like big thing. It's not. Let me show you. It's 2 lines of code. So we can solve, okay, which will do the next one. And then this will just keep repeating pretty much until it's done. However, let's say that it reaches, if possible, and it never returns true. So then it just moves on. Okay. So when we move on, it's going to say, okay, can't be there. We've already put it there. What do we do now? All we do for backtracking is we change the grid that we just created n previously. Same exact function, except instead of turning it into n, we're turning it back to 0, right? Because when it's 0, it will just try again with the next number. So this is all backtracking is. You're saying, hey, solve it if it's n, and then if it comes through here and it checks and it's like, wait a second, now it can't be that. So it goes through solve again, and then it says, okay, let's just change it back to 0 and try again. So where are we? No, okay. Yeah, we can just call return that first for loop. Just gonna paste in a really quick code here. I think we have a few viewers that sort of just watch, not intently. Boom. Okay, cool. So hot. Lol. All right, so there we go. That is the solve Sudoku. So this becomes the basis of our program, because this is cool and all, and this will work. But if I pull up a Sudoku puzzle and I want to solve this, I would have to put in every single space. I'd have to go 0 and then change this to a 4 and then 0, 0, 0. You see the problem? Like, it's not efficient. So we're going to address this right now. We're going to create 2 things. We are going to create an input section that allows the user to input the Sudoku puzzle, and then an output which will automatically solve the puzzle for you, and it will do it using PyAutoGUI, which is going to populate this whole screen for us, so we don't have to do anything. We just input the Sudoku, and then it spits out the answer and puts it in for you. Pretty slick. So to get started on that, we're going to start we're going to use this as our base. Okay, but we're not going to use the grid, so we're going to exclude the grid. We're just going to copy over this possible and solve into our new Python program. And then we're going to import PyAutoGUI as PG, and dang it. We're going to import NumPy as NP, and then we're going to import time. You'll see why we need that in a minute. So the first thing we're going to do is add our input section. Make sure I spelled all these right. Yep. Okay. So we're going to replace the grid by saying grid is equal to an empty grid. And then we're going to say, we're going to create a while loop. While true, the row is equal to the list of input, which will allow the user to input a new list called row into the grid. So it's going to be a list inside a list, just like we had before, except now we're able to populate each list. Okay, we're going to create an empty list called ints because we have to convert them to integers later. And we're going to say for n in row, we're going to say ints.append the integer of n, because it's going to go through each row number and then convert it to integers. And we're going to say grid.append ints, which. So all this is just a conversion piece, really. Inputs default as strings, and you can't in place convert this to an integer like that. You have to convert it later. So a lot of lists here. I could probably make a list comprehension out of this. I'm just really lazy right now. So recap, while true, row is equal to your input, which is currently a string. I know. And then we're saying, hey, for each number in that row, convert that number to an integer, and then append it as a list to grid. Because we can't have I mean we can, but we don't want a list. We don't want our Sudoku puzzle to be strings. We want it to be integers. And then we can break out of this by simply saying if the length of grid is equal to 9, which once it's done with its 9 rows and columns, or 9 rows, break. And then what I want to do as sort of a, I had this excluded at first, but I like it. So I'm going to say print, and then I'm going to say row, add the string of the length of the grid. And essentially all this does, plus the word complete. All this does is when we add a row, it will spit out and say row 1 complete, row 2 complete, row 3. So you kind of know where you are when you're adding it, because it's going to be slightly a terminal program. So all we're saying here is print the row plus the string of the length of the grid. Kind of confusing, but I promise it works. So that's it. That's our input. So what we've created right here is 90% of it. We just have to add the auto GUI part. Okay, so I'm about to enter in the last row, and it should spit out the answer for me. Boom, almost instantly. So we can check this by this, see if I put like a 4 here, it will be red. So if it's blue, it means it's correct. So I can just sort of copy this first line here. So this is how I had it originally. This is great and all, and this is the answer. However, it's not very efficient. It still doesn't feel like a program, really. It sort of just feels like cheating. Well, I mean, it is, obviously, but I wanted it to feel more like a program. Like you hit play, you enter in the numbers, and then boom, it spits it out for you. So I'm going to add a sleep function between the program running and when you enter it in. So it's time.sleep, 3-second lag. The reason I'm adding the lag in there is because I need some time to enter. I need some time between the time that I enter in the Sudoku puzzle and to click on the program that I want it to spit out. I mean, I could probably write another, yeah, it's cheating no matter how I make it. I know, but wait till I get to the end. It's better than cheating. All right. So under the matrix, so we're passing in the matrix, and then it's converting it right here. And then I'm asking it to append it to final. So final will be, it's going to be exactly like the grid from the first one. It's going to look just like this. That's what final will look like. Then I'm just going to say for lists, because it's going to be a bunch of lists inside of lists, in final. So I'm saying, hey, for each list, which there's 9 lists, and then I'm going to say for each number in the list. In lists. I'm going to append string.final append, which is an empty list currently. I'm going to append those numbers, but I'm going to convert them to strings. So now what we have is the exact same thing, final and string final, except string final is a string, which is what we want. I wanted to preserve final for whatever reason, but this is converting it. So now we need a way to stop it. And also we need a way to count how many have gone by. So I'm going to make another empty list called counter. And then we can say for num in string final. So for each time it goes through, 6, 4, 7, 1, 3, blah, blah, blah. We're going to say PG, which is our pg.press, which is our way of saying press the key. Press the key num. The way PyAutoGUI represents you pressing numbers is with the string version of that number. See? This is the problem I ran into the first time, because you can't press the number, it has to be the string. So if I want it to press the number 1, I have to represent it like this. So all I'm doing, instead of pressing in the string of whatever, I'm passing in num, which is currently a string thanks to string.final, right? So I'm passing in the string of whatever number it is in that list. Pretty simple. And then I'm saying pg.hotkey. We want to do left or right. Okay, so what this is going to do is it's going to press the number. Whoops. It's going to press the number, and then it's going to key to the right. It's going to press the number, key to the right, press the number, key to the right. You get the idea? So the problem I ran in with this was that I wanted it to go here, and then I could try to reverse index and separate this list and go this way, but I found it was easier to just key down 1, and then key left 1, 2, 3, 4, 5, 6, 7, 8, and then continue on. So to represent that, I'm going to start appending the numbers that I'm counting into counter. Now, since counter is currently represented as 0, if I check the length of it, it will grow by a factor of 1 each time I append it, which is obvious, but important to know, because I'm going to say if the length of counter mod 9 is equal to 0. So essentially, if it's divisible by 9 evenly without anything left over, which means if it's 9, if it's 18. So essentially what I'm telling the program is once it hits 9, or any of these are going to be mod 0. Okay, so I'm isolating this row by saying that. Then I'm just going to paste this in. I'm not going to type it out. I already told you what I'm going to do. We're going to hit down and then left 8 times. I'm sure I could do this in like a loop, but I'm lazy. Again. So what we're saying now is if it's mod 9 and it's 0, which is the end of every single line. Then stop this for loop for a second and do this, and then continue on. So it's gonna go boop, 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 boop. Oh, if length of counter is mod 9 and it's 0, which it is, then we're gonna do this. Down, left, 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 and then continue. Boop, 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 boop. Oh, if it's mod 9 and it equals to 0, which it is now, do this. Boop, 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 boop. You get the point. That's pretty much it. That's it. We've isolated the numbers into string final. It's gonna put the numbers in. Once it hits mod 9, it's gonna reset over here, and it's gonna keep going till it's done. So let's check it out. We have time sleep 3 here to give us 3 seconds between the time that we enter in the full puzzle and the time that we hit run. So I'm gonna put in the full puzzle. I'm gonna click on the top left corner, and then I'm just gonna sit back and watch my program go, provided I didn't screw up anything just now, which is definitely a possibility. So let's switch this to expert, and I'm gonna enter in our puzzle. All right, ready? Hit enter, click on the top, hands off. There we go. So a little bit of a lag time, but boom, it's done. 50 seconds. Oh, it's amazing. Oh, it works so beautifully. So for expert puzzles, I could probably, since the program needs a little bit of time to do all the appending, I could probably change this to like 1 second so we don't have to wait so long. But let's try that again. All right, here we go. Oh, right. I have to terminate because I asked it for more. Alright, here we go. Ready? Stupid ad. All right, hands up. Boom, look how quick that is. So yeah, we just gave it a 1 second lag time now, which is plenty. Done. 1 minute, 1 second. Yes. I would love this program now to go ahead and read the screen, and I could definitely do that with Beautiful Soup. So I'm not gonna do that today, but maybe I'll do that in the future. Beautiful Soup, we can basically parse data off a web page. So I'm sure those numbers exist in HTML. And then we could extract them and then solve the puzzles. So really, we could essentially hit go and then just wait, 10 seconds and it will just solve it, which would be amazing. So yeah, these are cells. Ooh, maybe not. You see how it's identifying pieces? Oh wait, maybe. We'd have to isolate a class. We'd have to find where for exists here. Probably the answer's in the code already, actually. Cell value. Ooh, it's not very clear. If this was just straight up numbers, it would be a little better, but this is a variable. Yeah, that's a project for another day. But it works pretty slick right now. Thanks for sticking around. There's still like a bunch of people in my chat that aren't talking, so if you're there, I love you all. Thank you very much. You're all very awesome, and I hope that I helped or at least entertained you for a little while. Well, we'll see you later. Bye.